I think one of the biggest problems that students have when it comes to the way in which I lecture is they write down everything that I put on the board. But then when you look back at that, that's not really telling you very much. So when you're writing out your notes, it might be better for you if you write down more of the things I say. I am not a PowerPoint teacher. I'm not going to have a PowerPoint that has all the exact wording I need you to have. You'll notice most of the things we learn in here are procedural knowledge, making decisions. It's hard to put that in a PowerPoint of things to memorize. Have you noticed how few things you have to memorize in here? Because it's not about that. Now, saying that makes it easy, but today there are some things that it would be very helpful if you wrote into your notes, and I might be a little bit more willing to be pointed at that. So, a projectile, by definition, is anything that moves in 2 dimensions, but is experiencing an acceleration in only 1 dimension. That's a projectile. It's anything that moves in 2 dimensions, but is experiencing an acceleration in only 1 dimension. So let's consider a simple example. And by simple, we're going to kind of work through what I mean when I say that. Although that is a definition for a projectile, it lacks substance. So consider just rolling a ball off a table. I can do better. A lot of people have this idea that the ball begins to fall after it realizes it's not on the table. So it'll go out for a little ways like a cartoon character, look down, see that it's no longer standing on the ground, and then fall. That's not really what happens. Right now the ball is being supported by the table, and the moment the table is removed, gravity pulls it down immediately. But the ball's already moving sideways. So some people kind of believe that the sideways part just changes and starts to point downwards. What I'm here to tell you first is that acceleration of gravity acts only downwards. But the ball's already moving sideways. What this ultimately means is that there's nothing to change the sideways motion of the ball. If the acceleration is downwards, it can't change how fast the ball is moving sideways. Remember, acceleration, by definition, is the rate of change of velocity. So a up and down acceleration can't change a sideways motion. So the ball, when it finally makes it to the ground over here, it's still moving sideways at the same speed it was moving at the top. Its sideways motion is not affected by the acceleration. That's a projectile. A projectile has 2 parts to its motion. It has sideways motion and up and down motion. And we work on them separately. Now, at some point or another, the ball is going to be, say, right here. When the ball's there, it will still have the same sideways velocity it's had. That part will not have changed. In fact, I'm going to label this x for the time being because it's the sideways velocity. It's in the x direction, so to speak. And we kind of have this commonality about what x is supposed to mean. But it's been in the air for a little while without the table to support it, which means that gravity has been acting downwards on it. Gravity acts this way, which means that after a short time, the ball is also going to have a y velocity. This is separate from the x velocity, in that the x velocity has not changed, but it's acquiring a y velocity. Try one of these things, right? Acceleration's acting on it in the downward direction. So I'm thinking one of these motion equations is probably working out on this one. After a few more moments, it's probably over here someplace. It's going to have a sideways velocity that still has not changed. But it's been falling for a longer period of time now, so its y velocity has changed. It's moving faster downwards, but the same sideways. Until finally it makes it right to the ground, and as it's hitting the ground, it probably has the highest y velocity that it's going to have. But it's still moving sideways with the same sideways velocity. So trying to emphasize this, the sideways part doesn't change, but the y part is changing the whole time. An object that travels in 2 dimensions, but experiences an acceleration in only 1. Now, that's kind of a lot to take in, and there's a lot to keep track of when you start to think about it. I kind of recommend a chart. You're going to notice I'm kind of big on organization when it comes to data. Not my life or my desk, but when it comes to data, I like to organize it. I see 2 parts to every one of these problems. I see a vertical part and a horizontal part. So I like to draw this T-chart out to remind me that there are 2 things for me to keep track of. Now in the vertical part, I'm going to have all of the same variables we've been having for a while. The object's going to have a vertical displacement. So instead of delta x, I'm going to put delta y. It's going to have an initial and a final velocity, but they too are in the y direction, so I'm going to put some y's there too. I know that that's a lot, but I figure it's better to be fully labeled and understand what I'm looking at than to be missing something. It's going to have an acceleration. This is very likely to be gravity, right? Probably 10 for most questions. Yeah, I know. We could put it on the moon or put it on Mars just to screw you over and make the problem harder. But there's already hard built into this. So I don't want to make the problem difficult in a non-purposeful way. Most of the projectiles, kicking a football, throwing a ball, squirting water, dropping something off the table, that's here in the classroom. That's going to be 10. So this is almost always going to be the acceleration of gravity. So it's almost always going to be 10. But there's also time. Still, these are all vectors. I think at the start of one of these problems, it's probably a good idea to draw 2 arrows in order to tell you what direction you're going to call positive in 2 directions. It might seem silly now, but be prepared. The problems don't have to be this straightforward. You kick the object off the table. Drop it from a plane that's diving. These are all kinds of projectile problems. Now, there's also the horizontal information. The object is traveling horizontally, so it's going to have a delta x. We know it's got a horizontal velocity, so vx. But there's no acceleration, so this one doesn't have initial and final. It stays the same because there's no acceleration. But it's going to have time. Now here's the thing. This is probably the important part. This is what you really want to pay attention to. Those have to be the same. That's really what a projectile is. It's moving sideways and up and down at the same moment. So the time of flight is the same for both horizontal and vertical. Now, if this were me and I were in a classroom and I was probably 17 years old, I would probably have all of this written in my notes and probably nothing else. It's at this moment where if you want to make this chart useful to you, you should tell yourself some things about this chart. I want to help with that a little bit. I'm not good at this because I kind of think I've said all the things I wanted to say. But you were listening, and then when I wrote delta y, you wrote delta y, and that was it because I moved on to the next one. So let's think about this because they're going to give you a ton of stuff. A guy kicks a ball at 30 degrees, and the ball leaves the ground at 40 meters per second. How far away does it land? And you're going to have to take that information and figure out where it goes here. I roll a car across the desk. The desk is a meter tall. How far away from the edge of the desk does it land if it was moving at 2 meters per second? That's a lot there, isn't it? All sorts of velocities and displacements, and where do they go? So let's talk about this. This is its change in height. That's going to be the change in height. So it's going to be things like how high the table was, or how high up on the hill you want to hit something. It's the change in height of the object. If you kick something from the ground and it comes back to the ground, it could be 0. But this is the change in height. So look for things like the height of a table or where the object's going to land. That's going to be what's there. This one is how fast it's traveling up it down. Sorry, how fast it's traveling up or down when it's launched. It's at the beginning. How fast it's traveling up or down when it's launched at the beginning. This one, I don't think they're ever going to give you this one. We never talk about how fast the football's landing. We don't say the guy caught the ball traveling at 100 meters per second. They say the ball left the bat at 100 meters per second. So it's very unlikely you'll get the vertical speed of the object as it hits the ground. It's the least likely thing to be given. So if you write a number for that one, you better be sure it goes there, because it's very unlikely you'll have that. I don't write problems knowing how fast it's going when it hits the ground. That's a person trying to create a problem that's not there. Right? They already know where it landed, so why give you that? You see the point I'm trying to make? We're trying to predict the future. Knowing the future doesn't seem like the place to start. Come on, we know this. This is very likely to be the acceleration of gravity. It's very likely to be 10. Or 9.8. Now, I think this one's pretty straightforward. The horizontal velocity is how fast it's traveling sideways. Many people take this and put it here because they're not paying enough attention to the differences. And we're going to try one in just a minute. But it's how fast it's traveling sideways. Yes, ma'am? We'll talk about negative and positive in just a minute. Now, the last one I really want to point out is this one. Delta x is how far away it lands. Often you could be given that. If you want to land something in a specific location, you'll need to have this. So be aware, you could be given this one very regularly. You know, I'm going to roll something off the table. I need it to land in a cup a meter away. How fast does it have to be leaving the table to hit the cup? That seems like not an unreasonable thing for me to ask for you to do, maybe on Friday. Now, at the same time, it also has another name. This is also called the range of a projectile. So when somebody asks for range, they're asking for delta x. I think time is pretty obvious, so I don't think I have to go through what that is. Time of flight. It's the same horizontally as it is vertically. So, here it is. You're going to roll a car off the table. Your tables are 86 centimeters tall. All of these are. You roll the car at half a meter per second. How far away from the edge of the table does it land? That's the question. I'll say it all over again. But you're going to roll a car at half a meter per second off the top of your table. Your table's 86 centimeters tall. How far away from the edge of the table does it land? This is example problem 1. And I would call, what I like to call this a type 1 problem. And you're going to grow to hear me say that because I like to highlight certain versions of projectile problems. In this version, the object is traveling with a constant horizontal speed at the start of the problem and no vertical speed. Now I'm going to say the problem again, and then I want to go through what I would do to solve a problem like this. Again, you have a car, you're going to roll it off the table. The car is traveling at half a meter per second, and your tables are 86 centimeters high. How far away from the edge of the table does the car land? So I'm going to get all this distracting stuff off of here. And I want to kind of go through a few things you should be thinking about. First, stuff does not take very long to land. So if you find that something takes 50 seconds to land, you're wrong. Nothing's in the air that long. Skydivers barely get a minute of time, maybe 2, before they're hitting the ground. So if you roll something off the table and you get like 4 seconds, you're wrong. There is no place in this room where you can drop something and it will take 4 seconds to reach the ground. So you should be prepared for numbers that are reasonable. Rolling something off the desk, it's going to take half a second or a second. Nothing in this room is going to be more than a second to fall, maybe 2 seconds from the ceiling. But I don't think we can get 2 seconds from the ceiling. Stuff falls fast. So just be prepared for that. Because I said that it fell 86 centimeters. What I was really saying is that the table was 0.86 meters tall. You'll forget to put that in meters. You'll put 86 because that's what was in the problem. And you'll find out that it takes a long time to fall, and that's not true. So that is my vertical. It is 0.86 meters. Now, you have to decide things about the vectors. You have to decide whether you're going to make up positive or down positive. Now, since I already drew the arrows in there, this means it fell downwards 86 centimeters. You'll know you made a mistake when you try to take the square root of a negative number. It's probably at this point you can just put that in your notes. If you ever try to take the square root of a negative number, you screwed up the direction. Because that's the only reason it shows up. I was hoping that would kind of come and hit you in the face by now, but if it hasn't, that's where taking the square root of a negative number has always come from. You didn't think about direction appropriately. Now, there's another one of these that's easy. Gravity, 10 meters per second squared. And it's downwards, so I'll make it -2. Now, here's the one that people are going to make mistakes on, which is why I'm trying to be really, really slow and deliberate. The car was pushed at 0.5 meter per second. So where does that go? You got 3 places where a velocity could go. So you have to know that if it's rolling on the table, it's rolling horizontally at 0.5 meter per second. That's what it means. The car wasn't rolling up at 0.5 meter per second. That doesn't make any sense. But you'll put it there anyways. Or you'll do worse, you'll put it that's rolling down at 0.5 meter per second. That's even sillier. Now, yes, every kid has run a car up and down on the wall. Well, maybe not every kid, but most kids who have ever had a car, they've run it on everything they possibly could have. But if you're just rolling it off the table, just like in my example, the vertical initial velocity is probably 0. Now, you are always trying to find the time. Always. That's the goal. Figure out how long it's in the air, because once you know how long it's in the air, you can figure everything else out. So you either have to have 3 pieces of information on this side in order to do that, or 2 pieces of information on this side to do that. You have to. And we've done this before now. Everything from this point forward, you've done. Find a relationship, plug the numbers in, get the time. And let me tell you, it's almost always going to be that second one, because it has all that initial stuff in it. So it's very likely you're going to be using delta y equals 1/2 at squared plus v initial y times t. Getting us used to the fact that up and down just changes those letters to y's. And in this case, negative 0.86 equals 1/2 times -10 t squared plus 0. I love a good solid 0 in a problem. Makes everything easier. Now, we are in closing minutes. T ends up being 0.42 seconds. Let you do the math on that yourself, but I'm sure you'll figure that it's 0.42 seconds. That part's not interesting. But it's what you do with it that is. It travels sideways 0.42 seconds. So the range range is always going to be the horizontal velocity times the time. Always. There's no other relationship here. So once you get the time and you have the horizontal velocity, it's pretty easy to find the range. In this case, it's 20 centimeters. All right, that's our first practice. This one, that's the one that's going to be the hard one, because that's the one that's going to have the angles and everything in it. Everything we've done all year in a single problem. You're going to love it. No, you're not.